So we are going to continue on with concepts of Riemann sums. Um, so the nice part about this is you are not actually going to have to calculate this. Okay, first, graph the function f of x is shown below. How can we approximate the area under the curve from -1 to 6? Now it does say create a Riemann sum with n subintervals and have n go to infinity. Okay, now the first idea is what happens if we have n is equal to 1? Now, you don't write this down. Okay, I'm just going to show you something we've kind of already breached, thought about. If I said n was equal to 1, and we are just, say, using the left approximation, because honestly, that's easier. So from 1 to 6, here we have this rectangle from 1 to 6. Okay, not a great estimation at all. Okay, well, if we have n is equal to 2, all right, that's going to keep that one. So there it is. But at what, halfway between there, which we, about 2.5. So right about here. So we'd have one rectangle right here and one rectangle right here. So a little better, at least we have, again, a positive value. And we do have a negative area here because it is below the graph. Okay. Well, what if n was equal to 3? All right, not breaking this into 3 parts. So n was equal to 3. That would give us what? About 2 1/3. So 1 up to here. And here. And there we go. So you kind of get an idea that as we progress, and we kind of reached upon this, as our value for n, as the number of rectangles increases, so if we had just an absolute ton of rectangles here, so as our values for the rectangles increases, the better our approximation is going to be. So even if we just had a bunch of small rectangles, actually this goes above. Did not mean to zoom in. So yeah, the more rectangles we have, the better the approximation is going to be. So the idea here is, well, how can I make the absolute best approximation? Well, that's when I have the number of rectangles be infinite. Right? So in that case, it becomes less of an approximation and more of the actual value. So now, if n is the number of subintervals, rectangles, on the interval from A to B, what is the width of each rectangle? I kind of just did that in my head here. What was the width from -1 to 6? Well, that was 7. So when I separate that at 2 intervals, I just divided 7 by the number of rectangles, by 2. So if I had 3, I divided 7 by 3. So the idea here is that the, what we call delta x, okay, which is our width, that is going to be your endpoints, the difference in your endpoints, divided by the number of rectangles. Now, if n approaches infinity, on the interval from A to B, what is the width of each subinterval rectangle approach? Well, what happens if we have the limit as n goes to infinity of b minus a over n of your width? Okay, what happens when you have infinity in the denominator? It goes to what? Yeah, 0. So width approaches 0. Now, how do we write the sum of all the area of all the rectangles under this curve? Well, the first rectangle would be delta x sub 1 times the height. Now, the height of each rectangle is based on the function, so that is f of x sub 1 plus delta x sub 2 times f of x sub 2 plus delta x sub 3 times f of x sub 3, and so on and so forth until we reach n. Oh, forgot delta. Delta x sub n times f of x sub n. Again, this is the area of rectangle 1, rectangle 2, where this is our width, and this is our height. Now, is there a way to write that in a much smaller manner instead of writing all that out and over again? Because again, if n goes to infinity, you'd never finish. Okay, so is there a way to write that? Yes. Have you guys dealt with summation notation before? Okay, a little bit. Again, should happen in pre-calc a little bit. Again, should doesn't mean it always does. But that is our summation symbol. All this means is we are going to start with our initial value. So we start at 1. So this says starting at 1, going to n. Okay, this is our start and our end. Okay, of our function. Now, if you know our function is delta x times f of x, we're going to write this a little differently. Okay, because we're going to write what delta x equals. Now, delta x equals b minus a over n. All right, and the function. Okay, now the function, because this is our height, is going to start at a. When we plug in a value into our function, we start at the initial value, okay, at a, and then we add our delta x, our change, our b minus a over n, okay? But how do we represent every single possible addition? Because again, that right there would be only adding one delta x. How do I add the next one, and the next one, and the next one? That's where this k value comes in. Okay, so that allows us to put this in summation notation because it's allowing us to plug in every new rectangle position. So again, this is our width. We're looking for area, and these are our rectangles. Width times height. Now, like I said, the nice thing about this is you are not going to have to actually do this. Okay, you're just going to be converting things back and forth. Now, if you want to see an example of this, right, let's say that f of x is equal to 2x plus 1, and my interval is from 3 to 5. Right? There's not a lot of room to write this here, so I'm not gonna worry about writing the summation notation. I'm just gonna write what goes inside the summation. So my delta x would be, again, the change from 3 to 5, so 5 minus 3 over n. And my f of x, k, really, because this is what's going to go in here, would be my initial value, okay, which is a, plugging it in for x. So that's what I'm going to plug in. So it's going to be 2 times my initial value 3 plus, again, 5 minus 3 is just 2 over n times k, and then plus 1. So if I wrote this as that summation notation, it would be the limit as n goes to infinity, summation of k equals 1 to n of 2 over n times what I just wrote up here. 2, 3 plus 2 over n k plus 1. And there's that summation notation. Now, normally, again, if I did have an endpoint, okay, if I did actually have an endpoint, I had a definite summation value, I could actually put that in my calculator. Because you can do summations in your calculator. It's the same place you do derivatives. Go to math, and you should find summation somewhere. It is summation. Okay. The difference here is if you know what n value is, you would have to plug in your values for n. So say if we had just 5 subintervals, we go from n was 5 rectangles, I would plug in 5 for every n. Again, you don't have to do that. So now, another way of writing this is instead of as n goes to infinity, we are going to look at what happens as delta x goes to 0. And it's honestly just the same thing. K equals 1 to n of whatever your delta x is times f of x sub k. Now, this is not used very often, but just in case it shows up on an AP exam, it is the same thing. And again, there's so much beyond this Riemann sum notation that there's not going to be a lot of importance placed on specifically this. You may see it like 1 or 2 questions, multiple choice questions. This will not be any of these pre-response questions stuff. All right. Next page. So this is what primarily is going to be your homework. Okay, is to do these conversions, is to convert your summation notation to what's called a definite integral notation. So if you have the integral from a to b of a function, we can write this using what's called integral notation. You have an integral. This is an integral. It is an elongated s. And the reason why it's an elongated s is because it's dealing with summation. Okay. A to b. Those are our bounds. Okay, we have our lower bound and our upper bound of whatever my function is times dx. Now, the dx is just letting you know what you're taking the integral of. It's kind of like how we have d over dx. We're taking the derivative according to x. Here, we're taking the integral according to x. The width is within the bounds. The width is found within the bounds. This right here automatically assumes that you have an infinite number of rectangles. So this is not going to have any type of estimation. This will be the exact value of the area under the curve because it's taking your bounds and making an infinite number of rectangles in between the two bounds. Okay, so your width is actually right here. And this is your height. This dx is more symbolic. Because there are cases where you're going to take the integral according to y or the integral according to t. Basically, it's just saying this is what we're taking the integral of. And if you do go beyond this, do you remember implicit differentiation, where you had multiple variables? You will have integrals involving multiple variables. And it's honestly a whole lot easier than implicit differentiation. So a lot easier. The real fun stuff is when you do double integration. That's when it gets tricky. So now, like I said, all we're going to do today is we're going to convert back and forth between your summation notation and your integral notation. So they want us to take this integral and write this as a summation notation. So as a limit as n goes to infinity of the sum of k equals 1 to n. Now the nice thing is that's how all these are going to start. So you can go ahead and have at least that written down. All right. Now, what is my delta x here? Since this is my b and this is my a, delta x is b minus a over n. So 6 minus 2 over n would just be 4 over n. Now, what we're going to plug in, x is going to equal a plus your b minus a over n times k every single time. So all you're going to do is replace every x value with that. In this case, what is my a value? 2. So we are going to write times, I'm going to put a bracket here, 2 plus 4 over n k. And since x is being squared, squared minus 3. And that is it. The conversion from integral to summation is real simple. Problem comes mainly with the conversion from summation to integral because there can be multiple ways to write this. Now, the nice thing is if you do see this on an AP exam, they will primarily be multiple choice questions. So you just have to figure out which one actually fits the summation notation. So now I'm going to just go ahead and write down the 3 answers. Okay. So I'm going to go ahead and write down 3 answers, and they are as follows. The integral from 0 to 6 of 4 plus x squared dx. The integral from 4 to 10 of x squared dx, which is the one I would think of every time. I would just do this is the most common one. Okay. And then there's the most typical one to come across. 0 to 1 of 6, 4 plus 6x squared dx. Okay. All of these are correct. So let's explain where we get each of these. Now, the thing is, if we look at what we set up here, x is equal to this right here, then what would you think that a is? Yeah, you would think a is 4. That's why when I did this, that's the first thing I came up with, because it gave me a is 4. And if my b minus a, because this is my b minus a, if my b minus a is 6, then what minus 4 gives you 6? So your b would have to be 10. That makes that b value, that answer would be real easy to come across. But how do we get this? This is not necessarily a. And if I misspelled that, that's fine. Okay, you know what I mean. So not necessarily a. Doesn't have to be a. It can be, but it doesn't have to be. Okay? So that means that my b minus a has to be 6, which means it could just be from 0 to 6. Okay? And I just have this right here as my x. Because if a is 0, then I would have this to be 0 plus 6 over n k. And why would I need to write the 0? I don't need to write the 0. I would just leave it as 6 over nk, which is what I have. Okay, and the 4 is just part of the function. All right. Now, like I said, this one, oh, don't do that. Why would you? Stop. So, like I said, this was the one I came up with first because if this is A, that means that b minus 4 over n is equal to 6, which means b is equal to 10. And then I can just say that this right here is a plus b minus 4 minus a over n, okay, which is 4 plus 6 over nk. So yeah, that the whole thing is plugged in for x squared. You really would just replace all of this with just x, and that would be it. That would be your whole function. Now, part C. Part C is a bit of a challenge. So we know, again, that x is equal to a plus b minus a over n. Okay? So what if that the 6 was really just a coefficient? So we could have 1 over n times 6. Okay, bracket of 4 plus 6. Again, if my a value is 0, I would write that as 0 plus 1 over nk squared. Got too many brackets here. Oh, no. Squared is outside. Now, simplifying that further, this would combine to 6 over n, which is what I have, times 4 plus, the 0 goes away, 6 times that is 6 over nk squared. So, yeah, that also works. Now, like I said, most likely this is going to be a multiple choice question, and you would just have to work out which one of these works, which one of these can't be true. Honestly, it's usually much easier to figure out which one's not true. To cancel out the ones that don't work, that's so much easier. Now, the ones on the homework, if they actually will have you do this, are going to tell you what the initial value is, that the lower limit of a is this. So you can easily find one answer for this, not multiple answers. Okay. Now, since right here, this is delta x and a is 0, my integral is going to go from 0 to what? 2. It's 2 minus 0 over n. So again, this is b minus a over n, which gives you b minus 0 over n is equal to 2 over n, so b does have to be 2. All right. Now, this right here, if we're looking at what's happening here, my function, because obviously it does have to be 1 over something. Okay, that should be pretty obvious. But what goes down here is my function, that's my delta, that's what I'm plugging in. My a value is 0. Since my a value is 0, I'm plugging in 0 plus 2 over n k. That's going in for x. That is equal to x. Or just 2 over n k is equal to x. Now, this is my k equals 1. Okay? This would be k equals 2. This would be k equals 3. What? So really, I'm just plugging in x. Now, we have a plus 3 to deal with. That's just part of the function. That plus 3 remains constant, so that's going to be part of the function. So you can see if we go from 2 over n to 4 over n to 3 over n, well, that's 2 over n times 1, 2 over n times 2, 2 over n times 3, and then 2 over n times n, all the way at the end. Now, you do have to read the questions carefully because number 3 tells me that assuming the lower limit is 0, right definite interval represents the above expression. This one says this is the expression is a Riemann sum approximation. Okay, the approximation means that we are not using n going to infinity. This has a certain set of n values. In fact, in this case, n is equal to 10. Because that is your denominator. N is 10. So we have 10 rectangles. Right? Now, if your b minus a is equal to 1, then really what this becomes is integral from 0 to 1 of just cosine x dx. Now, like I said, where is this in? Why is it written in the integral? Like I said, the 10 represents how many subintervals there are. Okay. Again, number of rectangles. It has nothing to do with the function. If that's it, was 50 instead, we would have a better approximation. Again, that's the whole key here, is it is an approximation. So if they're giving you a approximation, if they don't give you the summation notation, all right, then they're telling you that n is a value, and that denominator has nothing to do with your function, just how many subintervals that they broke this one into. So really, what this says is I'm taking the sum, the limit is gone, of k equals 1 to 10, okay, of what? 1 over n cosine of 1 over n k. That would be how you would write that specific summation. That's it for the first 7 notes. So let's go to the next page. Now, this is accumulation function, but we are also going to talk about the fundamental theorem of calculus, part 2. Okay. So we'll get to that. So last lesson, which was just a moment ago, we learned about the definite integral from a to b of fx dx represents the area under the curve on the interval from a to b. So let's say that we know the interval starts at a, but we do not know where it starts. That would give us an interval of a to x. Because we know the starting point, we don't know the end point. Where a is a constant, x is some unknown variable, we can represent a new function, and that looks like this. Now notice that this is a capital F. Okay, that capital F does represent a different type of function. So that is well, you'll see what it represents in just a second. That it is the integral from a to x of f of t dt. Now, do not confuse the t with time. There's nothing to do with time, okay? T is just a random variable, okay, used because we can't use x. Mainly, we can't use x because we already used x right here. We have x right here. We cannot have x down there. Okay, that would make no sense. Okay, so do not confuse that variable down there with anything. It doesn't represent anything specific. It's not time. Okay, people do that confused because usually we do represent it as time. We take the derivative according to time. When we do a lot of those other functions we dealt with. All right, just don't want you to get confused with that. Now, here's the idea. We are going to break this down, and we are going to say that my x value is represented by each of these numbers here. All right. So what this does, since again, this represents area under the curve, all of this represents area under the curve, we are going to go and find the area from 0 to each of these numbers. Now, that means if I have the integral from 0 to 0 of f of t, all right, that would just be this line here. Does a line have area? No. That kind of does bring up something we'll talk about later on. If your lower and upper bound are the same, your integral is 0. Now, if we go to 1, that will be from here to here, and we can just count the number of squares. So we have 1, 2, and a half. So 2.5. All right, so 1, 2, 3. All right, if we go from 0 to 2, we are adding in this little section, so we're adding another 1.5. That gives us 4. We go to 3, that gives us this section, adding another 1. Go to 4, it gives us this section, gives us 5.5, adding another half. And then down here, this is a negative value because it's below the x-axis. We're taking away half, so back to 5. So if we were to represent this function graphically, we would have a 0 function here. At 1, we would have 2.5. Right? Then we would have 4 at 2. Then we would have 5. We'll go a bit off the graph here, and then back on. So this is called an accumulation function, which honestly the title of the lesson should kind of give that away. All right. Now, this is the fundamental theorem of calculus, part 2. You might ask, when did we ever learn the fundamental theorem of calculus, part 1? And we haven't. Okay. The reason why we call this part 2 is because most textbooks actually teach this second. But the College Board, the AP website that we use, has this being taught first. So, yeah, they just reverse the order. It makes no difference. They're connected, but it really makes no difference what order we teach in. And this is kind of the simpler part of the two. Usually it's in the books, it's kind of more of an afterthought. But College Board does place a little bit more importance on this. So that's why it kind of comes first. All right. So this is the fundamental theorem of calculus part 2. d over dx, represents the derivative. We have our integral. So we're taking the derivative of our accumulation function. Okay. So this is the derivative of capital F. So capital F of x. Okay. Or capital F prime of x. Okay. Now, what this actually equals, what our final result is just our original function, f of x. Now, that means that if we take the derivative of an integral of a function and we get back to the original function, well, that means derivatives and integrals are what to each other? Inverses. They are inverses of each other. They cancel each other out, just like multiplication division. Example 1, the graph of f is derivative of capital F of x. So capital F of x is considered to be the antiderivative. Antiderivative. That's going to be kind of an important word we are going to use on Wednesday when we pick back up. Okay. Now, what does this mean? How are we going to see this represented on the AP exam and on test and homework? All right. We are going to have an integral. Okay. And now, if you just had any function, if we had d dx, so if we just did d dx from the integral from 0 to x, like honestly, this by the way, means nothing. This just must be constant. It does not matter what constant value that is. It could be 1,000,000, it could be pi over 2, makes no difference. Okay, going to x of any function. So we can have any function. We have t squared minus 5t plus 6. All right, dx, or dt, not dx, dt. All that's going to happen is everything gets replaced with x. X squared minus 5x plus 6. That is it. They just cancel each other out. The derivative and the integral cancel each other out. The difference is my upper bound, because I'm going to x. I don't know what x is, but I'm going to x. That's what gets replaced. My random variable gets replaced with my x value. So I'm going to kind of go to the next page here. We're going to kind of jump back and forth here. So what would my answer be if I wanted to find f prime of x, if I wanted to find the antiderivative of this? Okay, since, again, that 2 doesn't matter. I'm going from 2 to x. All I'm going to do is replace t with x. 3x squared plus 4x, and that is it. Okay. The whole idea is you're kind of getting the understanding that derivatives and integration cancel each other out. Okay. Now, the real fun stuff is what happens when your upper bound isn't just x? What if it is a function? What do you think you're going to do? I have a guess. We're taking derivatives, and I have a function within a function. What do we do when we have functions within functions? Chain rule. So going back to your previous page, if my upper bound is a function, we are going to plug it in, f of g of x. That is going to be part of it. We do plug it into the function, times the derivative of my upper bound. Okay, so let's look at this played out at number 2. So here, this is my g of x. Again, I don't care what the lower bound is, because as long as it's constant, I'm fine. Okay, so f prime of x, we are going to plug in that x cubed into here. So that is sine of x cubed times the derivative of x cubed, which is 3x squared. Now you can write it as 3x squared sine of x cubed. All right. So number 3 is very similar. It's just we have a separate function here. Where, again, we are going to put that in there. So we take the derivative, capital, again, the derivative of capital f of x. That is going to give me h of 4x times the derivative, which derivative of 4x is just 4. So we can write that as 4 h of 4x. Now, 4 and 5 are a bit different because my lower bound is not just a simple constant. So what happens when your lower bound is not a constant? Just so you note this, if you do happen to see this, if I happen to see the capital F of x is equal to the integral of x to a constant. Okay, so let's say just constant of f of t dt, then that can be rewritten as negative integral of a constant. We'll probably see this later on of f of t dt, and then we do the same thing. Okay, so if we have your variable in just the denominator and your numerator, just your lower bound and your upper bound's a constant, you can flip it, but you have to make your integral negative. Okay, just in case. I don't know if you're going to see it in the homework, okay, but just in case. That is usually what I've seen when I've taught this lesson is something like that. But what happens if both your lower and upper bound are variables, are functions themselves? So that's the second part here. Now, it's really not too bad. It is going to be this same thing. It is going to be f of g of x times g prime of x. But the second part is minus f of h of x times h prime of x. So you would just subtract the two bounds. You plug them both in just like you would with the upper bound. The change here is that it is minus between the two. So let's see this in practice. Again, this is my function, so f prime, capital F prime of x would be, again, I'm going to plug that x in here, so 5x times derivative of x, which is 1, minus, here this is 5 times negative x, times this derivative, which is negative 1. Now, that's a lot of negatives there. This first part, that is just 5x. But I have 1, 2, 3 negatives, which means the whole thing is negative 5x, and 5x minus itself is 0. Do you remember your even and odd functions? You know, the whole idea of symmetry between even and odd functions. So your even functions have mirror symmetry over the y-axis, reflective symmetry over the y-axis. Odd functions have rotational symmetry around the y-axis. Graphically, 5x is pretty simple. Again, that just means you have a slope of 5, so it's pretty severe. But if I'm going to the same distance, x and negative x on both sides, and I'm finding the area, what's going to happen to those two areas, since one's above and one's below the x-axis? They're going to cancel out. That will be one of our rules. If you do have an even function, and you're going from negative a to a on your bounds, your integral will be 0. I'm sorry, if you have an odd function, your integral will be 0. If you had an even function, because it's mirrored reflectively, it'll just be twice the integral from 0 to x. Again, something we'll see later. I just like to talk. All right. So next one, last one. Same concept. We are going to plug in 3x here. So f prime of x. We have parentheses 3x squared minus 3x times the derivative of 3x, which is 3, minus parentheses 2x squared minus 2x times its derivative, which is 2. Try that better. Simplifying that, 3x squared gives you 9x squared minus 3x times 3 minus 4x squared minus 2x times 2, squared times 2. So it gives you 27x squared minus 9x minus 8x squared plus 4x. And that